Hello and welcome to Chapter 7A Pound Bank, talking about angular kinematics. So we start with number one, a grindstone spinning at the rate of 8.3 revolutions per second has what approximate angular velocity? So here we are looking at just a conversion. We are given a rotating rate of 8.3 revolutions per second. Our unknown is how many radians per second that is. Our equation would be 1 revolution is equal to 2 pi radians. So we'll call it substitute, but we are just converting 8.3 revolutions per second. We're going to multiply that by 1. And anything divided by itself is 1, so we can say that 2 pi radians is 1 revolution. Again, these two things are equal, and anything divided by itself is 1. This is equal to 16.6 pi radians per second, which is equal to 52.14. Just call it 52.1 radians per second. Number 3, a Ferris wheel starts at rest and builds up a final angular velocity of 0.7 radians per second while rotating through an angular displacement of 0.49 radians. What is average angular acceleration? So we are given our omega initial is equal to 0. Our omega final is equal to 0.7 radians per second. Our delta theta is equal to 4.9 radians. Our unknown will be our angular acceleration, or alpha. Our equation looks like we can use, we have theta, we have final and initial. We do not have time, so it looks like we will be using omega final is equal to, omega final squared is equal to omega initial squared plus 2 alpha delta theta. Substituting everything in, we have 0.7 squared is equal to 0 squared plus 2 alpha times 4.9 radians. Let's divide by 9.8. Divide by 9.8. Our solution will be 0.7 squared divided by 9.8. So alpha is equal to 0.05. Let me write that the other way. Radians per second squared. Number 5, A turntable has an average angular acceleration of 1.5 radians per second squared. And an initial angular speed of 3.0 radians per second. Was the turntable's angular speed 4 seconds later? That 4 seconds is our delta time. Unknown is omega final. Our equation, we do not have theta, so it looks like we can work with our final angular velocity is equal to our initial angular velocity plus our angular acceleration times the amount of time we go through that angular acceleration. So substituting everything in, we already all set up, and we have 3.0 plus 1.5 radians per second squared times, forgot to write that down, times 4 seconds. We see here that our seconds are going to, our second squared and our seconds are going to cancel. So we have 3 radians per second plus another radians per second. It looks like an 8. And calculating that, we have omega final is equal to 1.5 times 4, looks like it's going to be 9, plus 3, 9.0 radians per second. Number 7, a Ferris wheel rotating initially at an angular velocity of 0.5 radians per second. So G is 0.5. This is omega initial. Accelerates over a 7-second interval. So delta T is equal to 7 seconds. At a rate of 0.04 radians per second squared, alpha is equal to 0.04 radians per second squared. What is its angular velocity after this 7-second interval? So our unknown will be our omega final. Our equation, looks like we have time, initial omega, and alpha. So let's find the equation that does not have theta. Looks like we'll use the same one that we just did. And we have omega final is equal to omega initial plus alpha times time. Substituting in, we have 0.5 radians per second plus 0.04 radians per second squared times 7 seconds. Solving, 0.04 times 7 plus 0.5 is equal to 0.78 radians per second. Number 9, a 3-meter radius automobile tire rotates how many radians after starting at rest and accelerating at constant 2 radians per second squared over a 5-second interval. So we are given a radius equal to 0.3 meters. Our omega initial is equal to 0 because we are starting at rest. We are given alpha of 2 radians per second squared. And we are given delta t is equal to 5 seconds. Our unknown is delta theta. We want to know how many radians we're going to rotate. Our equation is going to be, we have an initial angular velocity, we have an acceleration, we have a time. So it looks like we can use delta theta is equal to angular times time, angular velocity times time initially, plus 1/2 angular acceleration times the time squared. As you'll see here that we did not need the radius. Doesn't matter if we're dealing with a automobile tire or a monster truck tire. The fact of the matter is we're looking at its rotation. And even on a monster truck tire, any part on that fixed radius is going to rotate angularly at the same speed or velocity or angular velocity. So let's substitute everything in. We already solved for what we need. And 0 times t will be 0 plus 1/2 2 times 5 squared. Solving that, we have 25 times 2 is 50. We'll say then 25 radians. You take a look at the units real quick. We have here we have radians per second squared. Here we have seconds, but we're squaring it, so that's also going to be seconds squared. That's going to cancel out that, left with radians. Number 11, the drive wheel on a vacuum pump has an angular displacement of 158 radians. So given theta is equal to 158 radians. As it accelerates from rest to 70 radians per second, so omega initial equals 0, omega final is equal to 70 radians per second. What is the wheel's angular acceleration? So our unknown is our alpha. Our equation, we do not have time, so it looks like we can use our final. Omega final squared is equal to omega initial squared plus 2 alpha delta theta. Substituting in, we have 70 squared is equal to 0 plus 2 alpha 158 70 squared, 4,900 is equal to 2 times 158 at 316 alpha divided by 316 divided by 316. The solution is going to be 4,900 divided by 316, or 15.5 radians per second squared. All right, last one for tonight. An automobile's engine's angular speed is increased from 1,200 revolutions per minute to 3,600 revolutions per minute in 12 seconds. What is the engine's angular acceleration radians per second squared? So we are given some things that are not in the units that we're accustomed to seeing, so we'll have to change that. We'll start with our omega initial is equal to 1,200 revolutions per minute. So let's first change that to radians. There's 1 revolution for 2 pi radians, and there is 1 minute per 60 seconds. So 2,400 divided by 60, 40. So 40 times pi is 125.6 radians per second. We are also given omega final is equal to 3,600 revolutions per minute. We'll do the same process here. 2 pi radians for 1 revolution times 1 minute per 60 seconds. $7,200, that's 120 times pi. That is 376.8 radians per second. And we are given delta t, which is equal to 12 seconds. Our unknown is our alpha, our angular acceleration. Our equation, we will use the one that does not involve theta, which looks like it's going to be omega final is equal to omega initial plus alpha times time. Substitute everything in. We end up with 376.8 is equal to 125.6 plus 12 alpha minus 125.6. And it looks like we're going to have 251 is equal to 12 alpha. Divide both sides by 12. And we get alpha is equal to 20.9 or 21 radians per second squared.